and how this Zener diode is working as a voltage regulator, we will see that. So Zener diode is one of the type of diode that basically works in reverse bias. Okay, so here we have already seen the Zener breakdown and avalanche breakdown. So in Zener breakdown, we have seen like the Zener breakdown occurs when we are applying smaller voltage across the diode in reverse direction. So if we are reverse biasing the diode, it will be entering into the breakdown region, and this breakdown region will be working here as the main principle of operation in case of Zener diode. So the Zener breakdown uh, phenomena will be advantageous in case of Zener diode. Basically here we will be using the characteristics of Zener breakdown to make a Zener diode reaching into the Zener breakdown or breakdown region. And once the Zener diode reaches into the breakdown region, the voltage across this Zener diode is constant. So the voltage will be constant once it will be reaching into the breakdown region. So here we'll be using the Zener diode such that we are going to reverse bias this Zener diode, and once it reach into the breakdown region, its voltage across its diode, the diode voltage will be a constant voltage even if we are increasing the input voltage. So this property of Zener diode is being used as a voltage regulator. That means once it is reaching to the breakdown region, whatever voltage across it Zener diode is there, that will be become constant, and the same voltage will be appearing across the load resistance. So we will see this property of Zener diode and use it as a voltage regulator. Okay, so basically here this Zener diode is used to regulate the load resistance or load voltage, we can call it. So it basically it regulates load voltage. So whatever load resistance we have applied, so the voltage across this load will be regulated by this Zener diode. So this regulation will be appearing across the Zener diode. That means the configuration that we will be using is like we will have a resistance, and here we will be applying a input voltage. Okay, so this input voltage will be passed to a resistor, and a reverse biased Zener diode will be there. So the symbol of Zener diode is like normal diode is this. So this is the normal diode. So at the end of this diode, once we are going to make it a Z-like structure, so this is the symbol of Zener diode. Okay, so here this will be P side and this will be N side. Okay, so to reverse bias this Zener diode, we need to connect positive on this N type side and negative in the P type side. So similarly here, this is the Zener diode, so its symbol will be this. So this will be indicating the Zener diode, and this Zener diode is reverse bias because we are applying the positive voltage here. So this is positive and this is negative. This positive is connected to the negative side, so it is reverse bias. So we will be having a resistance in series with this Zener diode, and across this Zener diode, that means parallel to this Zener diode, we will be connecting the load resistance, and the voltage across this load resistor will be your output voltage. Okay, so this is the basic structure of uh, voltage regulator circuit uh, used by Zener diode. So this resistance R here is called limiting resistance. Limiting resistance. This is load resistance and this is limiting resistance, and this is Zener diode. Okay, so this is the basic structure of Zener diode used as a voltage regulator circuit. So here we have seen like in the power supply block diagram, we have already seen. So once we are getting the rectifier output, that is passed through a filter. So once we are going to pass through a filter, output that we will be obtaining through a filter is like, it will be a DC, but this DC will be a unregulated DC, means there will be some AC uh, component into this. Once we are going to have the output basically, so this is the output of uh, filter circuit. So we need to compensate, or we need to stabilize this output to have a DC output. Okay, so that means we need to have a regulation. So that's why we will be using a regulator circuit. Okay, so this is this Zener diode as a voltage regulator. Basically we can write here like, it maintains basically maintains a load voltage. It will basically maintain a load voltage that will be like, it is almost constant, or we can call it like, it will be independent of any load variation and input fluctuations. That means if this load voltage, that means output voltage, if we are varying this output resistance, with respect to that there will be some variation in the output, but this voltage regulator is going to maintain the constant output voltage even if we are reducing or we are increasing, or that means we are making a variation in the load resistance. Also if we are maintaining this input voltage that is varying between minimum and maximum, then also the output voltage would be constant. So this is the role of a voltage regulator basically. So there are, based on the variation, like based on the variation in the input voltage and based on the variation in the load resistance, so these two parameters can be varying in this configuration. The voltage across this diode will be constant. Okay, and we need to have output voltage constant, but the parameters RL and V input will be the varying parameter. So based on these two variations, we have two terms that is basically defined. So one term is called line variation. So line variation means if input voltage is varying, okay, and at that time with respect to the variation in input, what will be the variation in output? That analysis is called line variation analysis basically. So here it is like variation in output voltage, that is V naught, due to variation in line voltage, or we can call it like input voltage, that is Vi. So this analysis is called line variation analysis. Next one is a load variation analysis, or we can call it like load variation. So load variation will be because of the variation in the load resistance. Okay, so that means it is variation in output voltage, that is V output, due to variation in load resistance, that is RL. So these two terms uh, can be asked in objective type questions sometimes. Okay, so we should be having the clear uh, understanding of line variation and load variation. So line variation means if input voltage is varying, with respect to that some output variation will be there, that will be called line variation. Load variation means the load resistance is varying, with respect to that output voltage will be varying. Okay, the next we will see like how the Zener diode is basically going to be used as a voltage regulator. So we will see. So the basic we will see is what is the characteristics, VI characteristics of a practical and an ideal Zener diode basically. So if it is an ideal Zener diode, in case of ideal Zener diode, when we are varying, so suppose this variation is with respect to the voltage across this Zener diode and the current across this Zener diode. So here is like the variation will be like once it is ideal, it will be like once there is a new in forward bias, it will be similar to the normal Zener diode, normal diode that we have. So in forward bias region, once it reaches to threshold voltage, it will be having a sudden increase in current. In reverse bias, or this is if we know the exact diode. So in ideal diode is like once it is zero, we have applied a get drain voltage that is zero, that is voltage across the diode. So if the voltage across the diode is zero or just greater than zero, it will be on, and at that time there will be a current flowing through it. In the reverse bias, it will be like once we are applying the voltage that is less than zero voltage, then it will be in reverse bias, and there will be a voltage called breakdown voltage at which the Zener diode will be turning on. That means once it is turned on in breakdown region, it will be having a sudden current in the reverse region. So this voltage is basically called, this voltage will be called as breakdown voltage. In case of Zener diode, it will be called as Vz. So Vz is the voltage across the Zener diode, and if we are increasing this Vd value beyond this Vz, then also the voltage across the diode, Zener diode, will be always constant. Okay, so these are the characteristics of uh, Zener diode. So in forward bias, so if it is forward bias, this Zener diode will be replaced by an equivalent circuit. So this equivalent circuit will be replaced by like, so this Zener diode can be replaced as a constant voltage source that will be equivalent to the knee voltage, whatever knee voltage is there. So in this case, if it is ideal one, the voltage across this will be like a zero. So Vd will be zero. Okay, or if we consider some threshold voltage, some knee voltage is there, so it will be having a constant current at some threshold voltage. Okay, so we can have like this also. Okay, so there will be some knee voltage. So this knee voltage will be coming across here. So there will be, it will be replaced by an equivalent voltage source in forward bias. That was the case in case of practical diode. In the reverse bias case, this is the region. In this region, basically this diode will be in reverse bias. So once it is in reverse bias, this diode will be working as a open circuit because it is reverse bias. And this region is basically called breakdown region. So in this breakdown region, whenever we are going to have apply this drain this diode voltage greater than Vz value, this diode will be going into the breakdown region. So once it is entering into the breakdown region, it will be represented by a constant voltage source that will be equivalent to the Vz value, that will be the breakdown voltage. Okay, so beyond that, it will become a constant voltage source. It will be replaced by a constant voltage source. So this is the Zener diode. In breakdown region, it will be replaced by a constant voltage source that will be this, and the voltage will be Vz. So this breakdown region property we will be using here basically to use the Zener diode as a voltage regulator circuit. Okay, so this equivalent circuits of a Zener diode can be used in further analysis also, if it is used anywhere into the circuit, you can just replace if the general diode is an ideal. If it is ideal, it will be replaced by forward. In the forward region, it will be replaced by just a short circuit, you can say 0 voltage, or it will be having some cutoff voltage or knee voltage. Then there will be a voltage source replaced, otherwise it will be a constant voltage, that is 0 voltage once it is on, or we can call it is a short circuit in case of forward region. Once it is in reverse bias up to Vz, if we are applying the voltage between 0 to Vz, it will be an open circuit. But once we are applying voltage greater than Vz, here in this region, it has reached into the breakdown region, so it will be replaced by a constant voltage source even if we are increasing the voltage. Okay, but there is a limit also, like up to what we can increase this reverse bias voltage, uh, till the reverse bias the voltage in reverse bias voltage beyond Vz, till it gets breakdown. That will be the limit. Breakdown means it gets damaged, so we need to uh, limit to our reverse bias voltage also. That limiting will be based on the of power dissipation. So power rating of each of the Zener diode is given by Pz maximum. That means what is the maximum power rating it can withhold. If we are going to apply beyond this uh, maximum power rating, then this Zener diode will get damaged. So we need to limit ourselves in reverse bias voltage so that it could be less than the Pz value. That means this Pz value, or whatever uh, we are having the power dissipation across the Zener diode, like whatever Iz maximum is there multiplied by Vz, the voltage across this, and the maximum current it would be flowing, that should always be, you can say, less than, it can be replaced by, like, it should be always less than the maximum power dissipation it can have. So this is the property or rating of a Zener diode. So once this rating has been given, like maximum power, how maximum power it can dissipate, so we should be applying voltage or the current such that its maximum power should be less than the Vz maximum. Okay, so that you will be going to know into the next slides. Okay, so this was the case of practical diode, ideal diode. Now we will see the case of practical diode. So this will be the Vd, and this is the Id. Once we go with the plot, it will be like, in forward region it will be having like a normal diode. So in normal diode it will be like, so once it has reached beyond this knee voltage or threshold voltage, it will be having a constant current, current that will be increasing in exponential. So the current equation we have already seen in case of forward bias diode. So up to the knee voltage it will be having zero current, and beyond that it will be having a current that will be exponentially increasing. So this is the Zener diode in this is in the practical case of Zener diode. So in forward resistance, forward bias, it will be having a zero current till cutoff voltage, and beyond that it will be having an exponential increase in current. Similarly, in reverse case, it will be like, in reverse case, its current will be saturated to I saturation. So we have seen already. So this will be like I saturation current, IS. It will be flowing, that is a leakage current, or we can say reverse bias saturation current, that will be flowing through it, and there will be a voltage that will be called breakdown voltage. We have already seen. So breakdown voltage, so we will be applying a reverse bias voltage at the point where we are going to apply a reverse bias voltage that is equivalent to the breakdown voltage. Then there will be a sudden increase in the current. Okay, there will be a sudden increase in the current. So that increase will not be like maximum, but it will be going to a maximum value in this way. Okay, so that means this will be the point you can say this will be the voltage called breakdown voltage. Okay, so this breakdown voltage will be nothing but the VZ value, the voltage across this. But once we are going to increase the, it will be having some current I S we can say, or in the general diode case we can say like it is IZ. Okay. Similarly, if we are going to increase the voltage further, we will be having VZ1, and with respect to that, we will be having the current IZ1. Okay. Similar like if we are going to have a VZ2, we can have the current VZ, sorry, IZ, IZ2. It means this is the practical case. So instead of being constant, it will be having some variation in this general diode voltage. Okay, so generally once we are going to analyze, we will be considering the uh, constant voltage source. Okay, that means it is going to have a constant voltage source. This is the breakdown region. Okay, uh, and the region between here to here, this is called reverse bias, and this is the region where it will convert forward bias. So in forward bias, it will be behaving like a normal diode. In reverse bias, up to breakdown, it will be behaving like normal diode, but after breakdown, it will be behaving like a constant voltage source. Okay, so that constant voltage source will be equivalent to the constant voltage source that will be applied across the load resistance, and that will be giving the constant voltage or the regulated voltage. Okay, so this is the analysis, like how we will be analyzing. So basically we will be using this uh, ideal case. Okay, in most of the cases, or we can have a basic understanding, like in ideal case also it will be having some knee voltage, so that we can see based on the given criteria, whatever it is given, like it is ideal or practical. If it is practical, it will be having some knee voltage, and also the voltage, once it is reaching to a breakdown region, it will be having a constant voltage source, that is VZ value. So here the case, the similar case is already given here, so we can just analyze, like once it is in forward bias region, it will be equivalent to a voltage source. This is the case of like practical, we can just see there is a uh, there is a knee voltage. Okay, so this is knee voltage or cut-in voltage or cut-off voltage, we can just say. So this cut-off voltage, beyond this there will be a current flowing, so that will be replaced by a cut-off voltage in forward bias. In reverse bias case, it will be open circuit in case of breakdown region. So this is breakdown region. So in breakdown region, it will be replaced by a VJ2. Okay, so this type of analysis we are going to make to use a Zener diode as a voltage regulator circuit. Okay, so here once it is in breakdown region, it is having a constant voltage source. So voltage is constant, but current is increasing. Okay, so there will be a minimum current and maximum current. Okay, so once this Zener diode is having minimum current, okay, so in that case the PZ minimum, like the minimum power dissipation by the Zener diode will be equals to VZ multiplied by IZ minimum. So some minimum current will be flowing through this Zener diode, and the power dissipation, minimum power dissipation through the Zener diode will be given by like VZ multiplied by the minimum current flowing through this Zener diode. Similarly, the maximum power dissipation will be like PZ maximum will be given by like VZ multiplied by the maximum current that can flow through the Zener diode. Okay, so the maximum current that flow through a Zener diode is basically given by, so IZ maximum is given by like IZ M. So once Zener diode is given, in that Zener diode, the specification of Zener diode is like it will be given IZ value, sorry, VZ value. So what will be a VZ value? what will be its Vz maximum value and what will be its Pz maximum value. So these are the three specifications is given specifications given for a Zener diode. So for a Zener diode, these values will be given. So once these values are given, we will be applying the input voltage such that it should not be having the power dispersion beyond this. So if it is beyond this power rating, this is called a power rating that Zener diode is having. So we should be applying a lower power so that the diode should not be going to be damaged. So we can just write some points. So in case of Zener diode, how it is going to work. So in breakdown, basically once it is reaching to the breakdown, the voltage across it is constant, that is equivalent to Vz, and the current could be varying based on the input voltage. Whatever input voltage we are applying, with respect to that current will be varying. So here, so this Zener diode works in a reverse bias case. Also we can notice like acts as constant voltage source equal to Vz in reverse or in breakdown region. Okay, so it will be behaving like a constant voltage source, that is Vz, in breakdown region. So to make a Zener diode work as a voltage regulator, we need to maintain the condition like it is going to work in breakdown region. So we should be applying input voltage such that it is going to be working in breakdown region only. So once it is inside this breakdown region, then only it will be replaced by a constant voltage source Vz. If it is away from this breakdown region, then it will be like an open circuit, or if it is forward bias, it will be behaving like a constant, you can say the voltage normal diode that we have already seen the analysis of normal diode. Okay, so our main motive is to make this Zener diode work in breakdown region. Okay, so breakdown region condition, we will see like how we can maintain this breakdown condition. So basically here this is the basic circuit diagram that works as a voltage regulator circuit. Okay, so here what we can analyze is like, so suppose initially this Zener diode is, what we need to do is we need to reverse bias this Zener diode, and also we should be applying input voltage, and that input voltage should be turning this on. That means the diode should be turned on, so that this diode will be turned on when the voltage across this diode, so voltage across this diode we can call it. Okay, so just we can write like, we need to, our motive is we need to turn the Zener diode on. Okay, so our motive is to turn this Zener diode on, and this uh, diode will be on when the voltage across the Zener diode is greater than or equal to Vz. So voltage across this Zener diode is greater than or equal to Vz, then Zener diode will be on. Okay, so this is the condition, or this V, that is voltage across this, is nothing but the voltage across this resistor. Okay, or we can call it like VL. So voltage across this load, so we can write like V, that is equals to VL must be greater than or equal to VZ, then only this Zener diode will be on. Okay, so we need to maintain this condition to make this Zener diode on. Okay, so here we will, by suppose this is the condition, like if it is to find this condition, we should be considering like this Zener diode is uh, open circuit. Suppose this Zener diode is open circuit, and we are going to analyze the condition like how it is going to be behaving. Okay, so once it is just we can see like if it is voltage across this is Vz and that is equals to VL. So by using the KVL we can see here the current that is flowing through it. We can just find out like the current will be given like whatever the input voltage is there and the voltage across this. So VI minus VZ divided by R will be the current flowing through this resistor, or I, or we can call it like IR. So that is IR, that means the current flowing through this resistor, and the current flowing through this Zener diode is IZ, and the current flowing through this is IL. Okay, so this is one of the equation. Another one is like the current that is IR is equals to, by using the KCL at this node, we can get it is equals to IZ plus IL. So this is another equation. Okay, and also we can just see the IL will be nothing but the voltage across this load, that is ZL divided by the RL. Okay, and this VL is nothing but the VZ. So we can get VZ divided by RL is equals to IL. So these are the basic equations that will be used for the analysis of this circuit. Okay, so here we will go with the analysis, like how we can go with the condition. So there are different mode of operation or different conditions that basically defines how this Zener diode should be working. So the first case we will see. So our motive is to have this Zener diode in breakdown region. Okay, and to maintain this in breakdown region, we should be considering the different variations of RL and input voltage. So here in this circuit, so this is the basic Zener regulator circuit is there. Here this R is always constant. Okay, and the voltage across this will be a constant, but the current flowing through this will be depending on the whatever input voltage they are applying, and we need to maintain this output voltage a constant, or we can call it this load voltage that will be a constant. So this maintenance will be based on how the input voltage is varying. So this input variation can vary the output voltage, or this load resistance could be a varying. So into the circuit, so these two parameters can be a varying parameters. Okay, so with respect to that, we will analyze the circuit, like how we should be going with the analysis of voltage regulator circuit once any of these two parameter is going to vary. So any of these two parameter variation could affect the variation in the load voltage. So we will see that. So the first case we are going to analyze is like VI, that is input voltage, and the resistance, that is R, limiting resistance, is fixed. So this is the basic analysis. So if these two values are fixed, okay, then how the analysis of this circuit we can do. So the first step to analyze is, the first step is, first of all we need to determine like what is the state of Zener diode operation. So if Zener diode is working in what region, so we have the Zener diode could be working in three different regions. So one is forward bias, another one is reverse bias, and the next one is breakdown region. So first of all, we need to find out in what region this Zener diode is working. So the first step is to determine the region of operation of Zener diode. So the first step, we need to find out what is the mode of operation of this Zener diode. So once we know the mode of operation of Zener diode, now based on the mode of operation, we need to find out the voltages. So to find out the voltages, we need to substitute this Zener diode to its equivalent circuit. Okay. So once we know this Zener diode is working in forward bias, so once it is forward bias, we need to replace this Zener diode by its equivalent circuit. Once it is working in reverse bias, we need to replace its equivalent circuit in case of reverse bias. And similarly, in the third case, breakdown region, if it is working in breakdown region, we need to replace this Zener diode by its equivalent circuit, that is a constant voltage source. Okay, so once we know the region of operation, we need to substitute. We need to substitute uh, the equivalent circuit of Zener diode. Once we have substituted the equivalent circuit of the Zener diode, step 3 is now solve the network. So whatever network we will be obtaining, solve the network for unknown variables. So now we need to solve the network for the unknown variables. Okay. So these are the three different steps we need to follow to analyze voltage regulator circuit. So we will be proceeding with the first. So suppose this is the given circuit. In that given circuit, the input voltage and resistance, these two are constant, that is fixed, and we need to find out the voltage output voltage. Okay. So in that case, the first step we will be proceeding is to determine in what particular region this diode is working. So to determine the region of operation of a Zener diode, what we will be doing is we will be replacing this Zener diode by an open circuit, and we will find what is the voltage across this Zener diode. So that voltage, suppose that is equal to V. V is the voltage across this Zener diode. So we will find what will be this V value, and we will compare whether this V value is less than or equals to or greater than Vz value. That is the Zener diode voltage. Okay, that will basically decide whether it is working in what particular region. Okay, so the first step is we need to find the region of operation of the diode. So in that case, we have placed a voltage across this diode and make it open circuit. So we need to find out this voltage. So to find this voltage, we can just see this is, it is open, so there will be no current flowing. So the total current will be flowing in this circuit in this way. This is the current flowing through it. Okay, current. So from here we can just see the, if we find out the current, we can see like the current will be equivalent to equal to whatever the voltage is there divided by this resistance, total resistance of the circuit. So voltage is Vi divided by total resistance, that is RL plus R. This is the total resistance. This is the current flowing through this circuit. And once we need to find out this V, so that is equivalent to the voltage across this load resistance. So the V will be equals to voltage across this load resistor, that will be given by like the current flowing through this network and multiplied by the load resistance. So it is load resistance, that is RL, multiplied by the current. So current is Vi divided by RL plus R. So it is equal to like V is equals to RL by RL plus R multiplied by V input. That means this voltage is equal to RL divided by RL plus R into input voltage. Okay, so this will be the voltage that is obtained. So now we need to check whether this V voltage is greater than or equal to Vz or not. So we need to check like if V is greater than or equal to Vz. If this is the case, then Zener diode will be operating in on mode. Okay, and on mode means in breakdown region. Okay, so if this is the condition, we need to replace and we need to replace Zener diode by its equivalent circuit. The second case is like if whatever V voltage is we have obtained is less than Vz, then Zener diode is in off mode. Okay, and it will be replaced by open circuit. Okay, so if it is in off mode, it will be replaced by an open circuit. If it is on mode, it will be replaced by an equivalent circuit, that is a voltage source, constant voltage source in that particular case, that is equivalent to Vz. Okay, so we will be replacing this. So suppose it is in on mode. Okay, so the next step is step 2. Like if it is in on mode, working in on mode, then step 2 is we will be replacing its equivalent circuit, replaced by equivalent circuit. Okay, so that equivalent circuit is it will be replaced by a voltage source. Okay, so that voltage source is equivalent to Vz value, so we will be replacing it by Vz. Then now step third is now we need to solve for unknown variables. So now we need to solve this circuit for different voltages that we need to find, that is VL value, or what is the current flowing through it in the what is IZ, what is IL, what is IR, the current we need to find out now. So now with respect to that, we will be placing this VZ value in parallel with here. That means the VL value will be equals to VZ. So whatever load resistance is there, across this there will be a voltage, that is VL. So this VL will be equals to VZ because these two are in parallel. So this is the case if Zener diode is on. Okay, so thus first this we can obtain. The next by KVL, or sorry, by KCL we can get like IR will be equals to IZ plus IL. So IR, at this point we will be applying the KCL. So IR will be equal to IZ plus IL. Okay, so this is one of the case. Or we need to find out the IZ, then IZ will be equals to IR minus IL. Okay, and once we know the VL value, so once we know the VL value, we can get the IL. So IL will be equals to VL divided by RL, and we know the R value and the voltage across this we once we know. So IR value will be given by the voltage across this resistor VR. So this is like positive, negative. This is VR divided by R. This will be giving out IR. So once we know the IL and IR, we will be replacing here and we can get the IZ value. Okay. And now if we want to find out the power dissipation, so power dissipation across this Zener diode, power dissipation across uh, Zener diode will be given by like PZ, and this PZ will be equals to VZ multiplied by the IZ. So whatever current flowing through this Zener diode and the voltage across this Zener diode. So voltage across this Zener diode is constant, that is Vz multiplied by the current flowing. So once we know the Vz, we can put this value and we can get the Pz value. And this Pz should be less than the Pz maximum. So this Pz maximum is defined for a fabricated Zener diode. So that Pz value should not be greater than Pz maximum. Whatever Pz maximum is given, it should always be less than that. If this Pz is greater than, we can just say like, if Pz is greater than Pz maximum, Zener diode will get damaged. Okay, so we need to apply this Pz, so that should be less than Pz maximum. Okay, so this is the first case or the basic analysis of this Zener diode circuit. Okay, so the next three different cases are there. We will see that into the next class. Okay. So till now, if anyone is having any doubt, you can ask.